So now that we've seen how we can play around and view the graph of our second order differential equation by turning it into a system of first order equations, we're actually going to take another swing at this from a different angle. We're actually going to find equations for y of t, literally analytic solutions that solve our system. And we're going to use our old pal, a lucky guess. This one's a slightly different version, but it's along the same lines. We're going to do make an educated guess as to how to solve this. So we're going to start with our harmonic oscillator. And just as a reminder, the m, that stands for the mass. The b, that's the damping coefficient. And the k, that's the spring constant. Right? And the standard harmonic oscillator with damping looks like this: m times d squared y dt squared, the second derivative of y, plus b times the first derivative of y, plus k times y. And that's kind of standard procedure. And notice it's all equal to 0. We basically moved all the terms to the left-hand side. So what we're going to do is we're going to start off with this. And this is literally the model for damped harmonic motion. So if you have a harmonic oscillator with damping, you can use this model. You just have to figure out what goes in for mass, damping, and spring, and you can go forward. So for example, let's take a look here as we have three quantities: a mass, 2 kilograms. We have a spring constant, that's K, of 4. And notice the units on this: newtons per meter. Then a damping coefficient of 6 kilograms per second. And you might look at it and go, wait a minute, that doesn't look anything like what we were talking about before. It was newtons per meter per second. But you'll see it does work out in the end. So let's do a quick unit analysis and make sure that we're following the rules here. So we're going to start with our mass, and I'm just going to kind of translate this down here. So 2 kilograms times the second derivative of y with respect to t, plus b is 4. Oh no, sorry, b is 6. There we go, 6 kilograms per second times the first derivative of y with respect to t, plus k, which is 4 newtons per meter, times y. And all that has to equal 0. And we know that each one of these terms have to have the same units. So let's check and make sure what they are. So this is kilograms, and this is acceleration. It's meters per second squared. So that's meters per second squared. Now m here doesn't stand for mass, that stands for meters. And so what is a kilogram times a meter per second squared? That's a newton, right? This thing is defined as a newton. And so here we have just the units, kilograms per second times the velocity, and velocity is going to be in units of meters per second. And so you can notice that if you take a look at this, kilograms over seconds times meters over seconds gives me kilogram meters per second squared. And that, sure enough, that's also in units of newtons. And then this one is newtons per meter times meters, which is just units of newtons. And so they all have the same units. So that's good, right? So I'm going to make a little note here and say unit analysis. Shows these parameters work. If you, for some reason or another, had a mass in, I don't know, slugs or something like that, then you couldn't use them. It wouldn't work. If you had a B value in kilograms per minute, you'd have to do a unit change. You'd have to change things up in order to make it work. So checking the units is always a good place to start. So now that we know that the units work out, we're actually just going to write our equation, but I'm going to kind of shorten it down a little bit. I'm just going to write 2y double prime plus 6y prime plus 4y equals 0. And so what we really have here is an equation that says 2 times the second derivative of some function plus 6 times the first derivative of that function plus 4 times that function itself equals 0. Now, what kind of a function would work in this situation? Now, you might think, well, I don't know, maybe a polynomial would work. Well, second derivatives, first derivatives added to the original polynomial, it's going to be hard to make it work out so that it equals 0. So polynomial would be a pretty tall order. Other guesses you might think about are, sine or cosine. But as you can imagine, having a sine or a cosine, you're taking the first derivative and the second derivative, so that's going to get pretty complicated pretty quickly. So what the lucky guess method in this context is saying is we want some y of t that makes this true. And so we're going to try a guess. I'm going to scoot this up a little bit more, and we're going to try a guess. And since I've kind of avoided guessing it up to this point, you probably are sitting there thinking, hey, what about an exponential? And you're absolutely right. An exponential is the way to go here. So I'm going to guess y equals some exponential e to the some power of t. And so notice I'm going to say s times t. And the s is used there, not an a, not a b, but an s on purpose, and that'll make more sense later on. And so I'm going to say where s is just some constant that we don't know, but a constant nonetheless. And if this guess is correct, then its second derivative, 2 times its second derivative, plus 6 times its first derivative, plus 4 times itself, has to equal 0. So that means I need to know what's y prime. And so bring the s down. That would be s times e to the st, or sest. And then y double prime is going to be s comes down again, so we'd have s squared e to the st. And yes, that would be sest, if you wanted to say it that way. Yeah, you don't have to say it that way. And so we're going to check our guess. And the only way you can check the guess is by throwing it into the differential equation. And you're going to need both its first derivative, and its second derivative. So I'm going to go back to my brown marker, and I'm going to say, okay, well, 2 times whatever this second derivative is, which is s squared e to the st, has to be added to 6 times its first derivative, which is s e to the st, plus 4 times the guess itself, e to the st, and that has to be equal all to 0, right? If the guess is correct, then that has to be equal to 0. Well, there's something interesting that happens. Notice we've got 2s squared e to the st, 6s e to the st, 4 e to the st. So I'm going to factor out the e to the st here. And when I do that, I'm left with 2s squared plus 6s plus 4 equals 0 times e to the st. Now, you know a little bit of algebra, so you can look at this and say, well, there's 2 ways you can get 0 when you multiply things. It's if one of them is equal to 0 or the other is equal to 0. Or I suppose you could say both of them are. But interestingly here, e to the st, for any value of s, some constant of s, can't actually equal 0. So just as a side note, e to the st can't equal 0. So that means you're not going to get a solution from this being equal to 0. The only solution that's possible is coming from this polynomial. So the only way this is true is if 2s squared plus 6s plus 4 equals 0. And with a little bit of manipulation, you can see that this is really just 2 times s plus 1 times s plus 2 equals 0. A little bit of factoring there. And that means there's 2 possible values for s that make my guess correct. One of them is if s equals -1, the other is if s equals 2. So there's only two ways this guess actually works out, and those are the two ways. And so after all is said and done, we can say that I'll call this one y1, e to the -t, and then this one I'll call y2, e to the -2t. These are two guaranteed particular solutions. Now, I want to be clear, what I'm saying here is they are guaranteed solutions, and if you were to go back and plug either one of those into the original differential equation up here, they both work. They both will, when you plug them in, they both equal 0. But they're both guaranteed, but they're particular solutions. They're not the general solution. They're the particular solution. And just to verify this, let's hop over to Maple and see what Maple says. And so we left off looking at the general solution for this crazy system, but what if instead we tried to do a desolve on this thing? So this is me doing desolve on my second order differential equation, and Maple says, hey, no problem, here's the general solution. Look carefully at the general solution. What do you notice? You remember our two solutions, our particular solutions? One of them was e to the -t, and the other one was e to the -2t. Turns out those are the building blocks for the general solution. And it's not a coincidence, not by a long shot. Turns out that we found a way to get to a general solution by lucky guessing two particular solutions. We can put them together like this. We're going to get to that more later, but for right now, just know that Maple can double check our work, and of course we can always verify that each one of our particular solutions is a particular solution that you could see from this. So if I let constant 1 be 1 and constant 2 be 0, then we'd be talking about my solution number 1. And if the roles were reversed and constant number 1 was 0 and constant 2 was 1, then we'd be talking about this particular solution. So the general solution pans out, and this lucky guess method really does work for giving us two guaranteed particular solutions. Okay, that gets us to the end of section 2.3. In the next section, we're going to be diving into more analytic methods for dealing with systems of equations. So it's going to be algebra and calculus and manipulating equations. But for now, that's all I have for you.